Continuing on with not chapter 11, but class 11, here's an example 314 using specific heat. I tried to make this, I made it a little more complicated than what's in the book, but basically we'll do what's in the book first, and then I'll add some complexity. So cylinder fitted with a piston has an initial volume of 0.1 cubic meters and contains nitrogen at 150 kilopascals, 25 degrees Celsius. The piston is moved, compressing the nitrogen until the pressure is 1 megapascal and the temperature is 150 degrees Celsius. During this compression process, heat is transferred from the nitrogen, and the work done on the nitrogen is 20 kilojoules. Determine the amount of this heat transfer. Okay, so first off, I'll say that I'm not 100% sure I agree with this 20 kilojoule thing that has happened, but it must have, they said it, all right, so we're just going to go with it, with what they had, because I was looking at the enthalpy change, and I can't account for it. So first thing I'm going to do is maybe I'll write down some of the things that I have down. So we have nitrogen. The volume at 1 is going to be 0.1 cubic meters. State 1, the pressure is 150 kilopascals. And the temperature at state 1 is going to be 25 degrees Celsius. We could add 273 to that, and we will get 298 degrees Kelvin. Not a bad idea. In some of these problems. All right. And then state 2, well, we don't know the volume, but we do know the pressure, 1,000 kilopascals. The temperature is at 2 is 150 degrees Celsius, which comes out to 423 degrees Kelvin, if we need it. And work 1 to 2 is in. We might put that in there just to be clear, because its work is done on the nitrogen. Most of the time, remember, our work is coming out. So the work in is going to have a different sign to it. So we're going to try to find Q1 to 2. So first, maybe we could find the mass of this thing using the ideal gas law. So first we'll go to table A5 and find the constant R. And so we go to table A5, and I just flip right to it. And for nitrogen, where are you at, nitrogen? Right down there. And for R, let's see up there, we get 0.2968. And while we're here, we might want to check out CP and CV. We're going to need CV for this one, I happen to know. Might as well write both of them down, though. So while we're here, so here we go. R is equal to 0.2968. These are kilojoules per kilogram degree Kelvin. And then CP is 1.042 kilojoules per kilogram degree Kelvin. And CV, specific heat at constant volume, 0.745 kilojoules, whoops, I'm crooked, per kilogram degree Kelvin. All right, so from PV equals MRT, we can find out how much mass is inside this piston, because we're given what the volume is. We can find M is going to be PV over RT. And so that's going to be initial condition, right? Yep. So the P is going to be 150,000. The V is going to be 0.1. The R, I'm going to turn that into joules or Newton meters. So 296.8. And then the T needs to be in Kelvin, which we already did up here. So that's 298. Did I do that right? I think so. And I got 0.1696 kilograms. And I guess I decided just to go ahead and go with the basic one first. The basic approach. 1 to 2. So we could find this heat if we know the change in internal energy, and we're already given this guy right here. So let's rewrite this out. Q1 to 2 is going to be equal to U2 minus U1 minus W1 to 2. No, plus. Gotcha. Okay. But let's go ahead and use specific heats to find these U's, right? And if we go back to the definitions that we had, we will find, and let's see, I could go ahead and do that. And don't use this so much, but you can use these while you're doing an exam. So maybe I should talk more about the equations at the end of the book or at the end of the chapter. In this case, key concepts right here. They're using some of them. Should be reviewing these often. Maybe we should talk about them more in class. So here actually is the thing that we're going to use. CV, U2 to U1, it can be CV T2 minus T1. Right? This is for the ideal gas. Interestingly enough, that's the same as we have basically up here for solids and liquids. We just not really, and they say that the specific heat is basically the same. You don't really see that in the text as much. So this is kind of a little bit different written out back here. Useful to us. Things that we want to know written in the back here. So maybe we should be looking at these more often here. And they also describe some of this stuff, what to do with the tables. So not a bad place to look for things. But we're going to write this out right here, and we're going to use CV and the difference in the temperature. So that's going to be Q1 to 2 is going to be equal to mass times CV times delta T plus my W1 to 2. So the mass that we just got up above, 0.1696, CV 0.745. Notice those are in kilojoules right there, so we'll be on the lookout for that. And the difference in temperature, well, we don't need to use Kelvin here. We could just go 150 minus 25. And then here's a weird one, plus, but now we're going to go minus 20. All right, so you got to be careful and you're thinking about this, minus 20. Well, why is there minus 20? Because this is work into the system. Usually we use this right here. This is work out of the system. Since we're going in instead of out, we use a minus here. I know it's really weird. You just gotta take it on faith and accept it, that that's the convention, and everything will, no pun intended, work itself out. And so what you end up getting is negative 4.016 kilojoules. So that is the answer that's in the book. But I kind of wanted to go a little step further and kind of similar into what we did in the previous problem, which is to use stuff in the back of the book and the tables instead of using just these this right here. It says in the back of the book, or it says in this example, that you might as well, that this is a close enough approximation, because who wants to go doing all that interpolating? And of course, I don't necessarily want to do all that interpolating, but it did. There's a table for nitrogen. There's also another table. So it's actually, interestingly enough, we could and maybe I want to try to do this on the fly, we could use a table. All right, so I had a couple choices. First thing I did was to use the tables here, not F. I wanted to use B. Let's say B 6.1. So I went to B 6.1. So flip this around here. There's B 5, but here is B 6.1. So here's saturated nitrogen. But then I jumped over to here and found our superheated nitrogen. And if you go, and we started out at what, 150 kilopascals, so we're between. Oh, I think I just wrote down the wrong thing just a second ago. Did I write down the wrong thing? Nope, I didn't. Okay, so anyway, here's for 150 pascals is right halfway in between here. And the temperature is 298. So I went down to 298, so nearly 300. And I'm able to get what U and U is going to be, right? So I could take the average of those two, basically. Or I could do the interpolation of 298 in between. That's a lot more work to do a double interpolation because it's halfway in between here. And it's a portion of the way through there, right? There's 20 degrees in between here, and we're off by 2 degrees. So it's really going to be very close to this value. And full disclosure, I also tried the enthalpies and trying to do the same thing, but this is state 1, and I used those. I also used the specific the specific volumes right here to try to get as close as I could and to get the correct mass. And then they said they went to 1 megapascal, which is right here. And they had 423 degrees Kelvin. So what we do, 423 is right between 400 and, not right between, but nearly between. And so I had to do an interpolation there. Now, granted, it wasn't a double interpolation. It was just a single one because we were right here at the correct pressure, right in there. But I went in between there and found out what these values are, right? So if you want to see how I did the double interpolation, it was here's for specific volume, this is for internal energy, and this is for words are hard. This is for enthalpy. Shoo-wee. That was hard to say. And here's the you see here's the 298 where I'm doing it right here. So I do it between 100 and 200 and 100 and 200 to get the 150. So here's like for 280 degrees, here's for 300 degrees, and then down here. So I got the value. It's a lot of effort, but not if you've already have it set up. You're just plugging numbers out of tables. So here's the internal energy for the start of the thing. And then I did a simple interpolation here for the internal energy after. So here you go. There's one two. It started out at 220.5 and it ended up at 347. So you can take my word for it, maybe, that's what happened, right? So this is table B.6.2. So we end up with Q1 to 2. And I also found a new mass, by the way. I did the specific, from the specific volume that I found but for state 1, I was able to get a mass that was slightly different. So I got 0.5832. And then this is going to be, oh, by the way, I should write this out. Maybe above it. Okay, maybe I fit it in there. M times U2 minus U1 from the tables. And then I'll go the plus W12 again right there. So we'll just something to compare. So as I had stated, I got like, I think 312.81 minus 220.54. All right. And then I go plus a negative 20. And now the results of this is a negative 5.39 kilojoules. All right, so Maybe I trust that one more than that one. I think so, because I looked it up in the table. But they suggest that we use table A8. And I haven't tried that yet, so here's me trying to do that in real time. With the video's already 15 minutes, but let's try it anyway. But now I don't see it. But A8, that's why I can't see it, because I'm looking in B. You're looking in B, man. I got all the way to C, and I'm like, I don't know what to do with these. These are nitrogen, though, right? Nitrogen, nitrogen. Where'd you go, nitrogen? Oh, I'm looking at A9 for some reason. They have diatonic right here. Okay. So these are assuming like the pressure doesn't matter, which is actually true pretty often. And so we need the 298 for, and I'm not going to bother with enthalpy. Let's just start with him. All right, 222.63. So we will go to a simple 222.63. Let's see. I will cheat and go to a new page and just take my regular old interpolation here. Control C that, go over to here, Control V, and all right, so this is being fussy, I recognize, but we're gonna go 250, and this is gonna be 298, and this is gonna be 300, and so if you want to go in between there, you go 185.50 and 222.63, and you get, so this is going to be, whoops, you're still in what? Table B, no, A, excuse me, A.8. I guess it was just continued, right? They didn't really say what it was. So it's this guy right here. And what did I say? I said that U1 is going to be 221.145 kilojoules per kilogram. All right, now let's look at, we're going to have 423. So 423, so between here. So maybe I will, I got so many papers and stuff in the way here. No reason not to keep this. Should probably label what it is. So I'm gonna go 400. 423 is what we're looking for, and 450, and the values are 297.09 and 334.57. So we get 314.33. So I'll say U2 is 314.33. Take a look at these, the differences. We got small differences right here. Let's see if they make a difference. They don't have specific volume in here, so we're just going to have to decide which is the better of the ones that we have, whether it's the one from here or from right here that would pick our mass. Let's stick with this one for means. Well, I don't know. Let's stick with this one. Okay. So Q1 to 2 is going to be 0.15832 times 314.33 minus 221.145. That's a lot of digits. Plus negative 20. And we have a calculator somewhere? Sure. You don't need to see me plug numbers into the calculator. But you do need to get a reverse Polish notation. No, you're not going to do it. You don't want to listen to me, huh? You're just going to do things the way you want to do it. Like, okay, free will. What can I say? Your boss sees you have a Hewlett-Packard, and they know that you are a real engineer. All right, so we didn't change all that much. 5.247 kilojoules. Anyway, I just want to demonstrate that there were, this is an approximation, and there was other things that we could try to use to get a firmer number up onto the thing, and to see that we making an assumption by when we're using the constant specific heats.